Oops, I get a pen. Okay, so we are going to learn about doing atomic balances on chemical um, processes that have chemical reactions in them. And we're also going to learn about fractional conversion. So you should be able to perform atomic balances and learn to use information such as fractional conversion and yield to determine the output of a reactive process. So we hardly ever have to worry about atoms appearing or disappearing. They just form, the molecules disappear and appear. But the atoms are pretty stable in most of what we do. So we would, if we had a non-steady state process, we would have input minus output equals accumulation. And for a steady state process, we would have input is equal to output. So here's an example calculation. Butane is burned with air. If 1 mole per second of butane is burned with 40 moles per second of air, and we take air to have 79 mole percent nitrogen and 21% oxygen. Write the atomic balances for the process and determine the composition and flow rate of the furnace exhaust. So assume no butane in the exhaust. That means no butane in the exhaust. Okay, so there's no fuel left in the exhaust, which means that we have 100% conversion of the fuel. Okay. Yeah. Okay. So let's balance our chemical reaction. You can do this. You know how to do it. Butane burns with oxygen to form CO2 and H2O. Okay. What are the components in the furnace? Exhaust. Okay, so we want to write them. We're going to write the unknowns as mole fractions. We could also write them as molar flows, in which case we would not put an n dot in the top. Okay, and then we know that all the mole fractions add to 1. So the total gas out is n dot. Okay, so now let us, okay, this is explaining, this is now writing the streams in terms of molar flow rates. Here they are. This is actually redundant, but it's the total moles, so it's okay. All right, so now let's, when we write atomic balances, you should identify them before you write the balance. So we're going to write, and when you do your test, you should do C balance. Okay, and to calculate the C balance, we're going to put the carbon on the inside. Carbon going in is the butane, and the carbon going out is CO2. All right, and we have here 1 mole butane times 4 moles of carbon per mole of butane is equal to n dot of CO2, moles of CO2 per second. And it's implicit, but there's a 1 mole of C per mole of CO2. So that we're actually balancing carbon, not the molecules. So that ends up being 4 moles of CO2 per second. Now you should be able to do the other balances. I would recommend the second balance should be, well, you could do nitrogen, and you can also do hydrogen. All right, so nitrogen, it's very straightforward. In equals out. Okay, we've got this much going in, that much going out. Note that we multiply now 0.79 moles of N2 per mole of air. And this is, we leave N2 as N2. We don't need to split it down into N. Okay, so we have 31.6 moles of N2 per second. Hydrogen balance. We have hydrogen going in and hydrogen going out. Hydrogen is easier to do than oxygen. It's better to do everyone first, that you don't have to have any multiple equations and multiple unknowns. Not that you couldn't solve them, but we tend to make mistakes. So we're less likely to make mistakes if we just have a single calculation. So let's do the hydrogen balance. And we have 1 mole of butane times 10 moles of H is equal to n dot H2O moles of H2O per second times 2 moles of H per mole of H2O. That's an H balance. Okay? And we have N of H2O is equal to 5. So now we're ready to tackle the oxygen balance. O2 in is equal to O2 out. Okay, so we can either leave it as O2. Okay, so on this thing I opted to leave it as O2. Okay, so this is pretty straightforward. We have 21 moles of oxygen per mole of air. I'm sorry, 0.21 moles of oxygen per mole of air. And then we have oxygen in the water, in the CO2, and in the O2. So we have to incorporate all those terms where we have oxygen. And we end up with N of O2 is 1.9 moles of O2 per second. So let's talk about doing degree of freedom analysis. So atomic balances are the method of choice when you have multiple chemical reactions, and you may prefer to do them all the time. All right, so you should be able to do this degree of freedom analysis. So same as before, we write the number of unlabeled variables on the flowchart. So key here is having a clear flowchart. That's going to be very important on your test. Okay, number of independent atomic species balances. Okay, we had C, H, and O minus number of molecular balances, N. And then if we have any other equations relating unknown variables, and that will be your degrees of freedom. So let's see here. We have 5 unknowns. Okay. If we include the mole fractions, okay. 5 unknowns minus 3 independent atomic species balances, which are C, H, and O. And we have 1 molecular species inert, which is N2. Okay. And we have one other piece of information, which is the mole fractions add to 1. Pretty straightforward. So I don't think I really actually talked about it, but fractional conversion is simply the moles reacted divided by the moles fed. So how do we know how many moles were reacted? It's simply the moles that went in, and you subtract the moles that went out, and the difference is the ones that reacted, the ones that disappeared. Divide that by the moles in. Okay. The rest of the stuff we got, and we also talked about chemical equilibrium and atomic species balances, and now we are ready for our quiz. Okay, so you're just going to do on this little process here, you're going to perform atomic species balances. And so what we need to know is how much of everything is going in. Okay, so these are written as moles, not as mole fractions. Okay, so if we did the degree of freedom analysis, we would do, we have 4 unknowns. 1, 2, 3, 4. Okay, 4 unknowns. And we should write them. NW1, NE1, NET1, and NI. Okay. Then, so how many independent atomic species balances can we do? We can do 3. Okay. We have C, 3 balances. And these are going to be carbon, hydrogen, and oxygen. And we can do 1 inert balance. 1 inert, which is just inerts. Or we'll put them all together. Okay. So now we have 4 unknowns, and we have 1 inert. But we also have an additional piece of information, which is the fractional conversion. So we are going to talk more about this. You have the case here, what appears here, that we have um, uh, uh, too much information. Okay, and I could show you in a slightly more complicated way, but I won't, that in fact we need that fractional conversion. So, um, so th- we're gonna talk more about this, but this is the case where C2H4 is not independent of C2H5. So, um, anyway, uh, it doesn't really matter because if the alternative situation is that we have redundant information, and that is entirely possible. So let's just go ahead with the quiz. And what you're going to want to do first is use the fractional conversion. Okay. To determine um, the C2H4 that is entering. And then you're going to do a carbon balance to get the ethanol entering. And then you're going to do a hydrogen balance to get the water entering. You could do hydrogen or oxygen. It doesn't matter which. Okay.